Okay, it's 4:20. The person who is introducing people isn't here. Is the film, are we being recorded right now? Is the video recorded? So I can just start? I will just start. And it even is counting. There, it started. Thank you. Okay. Well, welcome back. I also need you to push the button to advance that. I think my button. Thank you very much. Okay, so welcome back. I gave a talk 2 talks ago about what is Hashgraph, and I just talked about the math stuff and the property stuff and how you might use it for identity. This is actually a master class right now. It's not a normal session. This is Developing for the Revolution, which was a master class track, not a normal session track. So the purpose of the next 2 sessions, which are glued together to form a double-length session, is if you are interested in building apps on top of Hashgraph, then this is how-to. I actually go through to how to build a Hello Swirlds app, and I show code, and I show architecture. So I just want to be clear, this is what this is, okay. But if you'd like to play with this stuff, this is a great way to do it. Download the SDK from our website. It'll be there soon. If you go there right now, you can sign up, and we'll send you a notification. Give us your email, and we'll send you a notification when it's ready to download. You can download the browser, and you can download the SDK, and you can just run our demo apps and see what they look like, and then you can write some apps of your own. And you can take the source code of our demo apps and modify it. And so today we'll help you with that. In addition, even if you have no interest in coding this, it is, I think, interesting to look at the architecture of what an app for a real-time distributed system would look like. Turns out there's some interesting quirks that you would want to put into an architecture in a real-time distributed consensus system that possibly you haven't seen before because no one's written apps for real-time distributed consensus systems. Bitcoin is sort of slow. Basically, if you want your app to be showing the user the current guess as to the transactions in their order, and then later reorder it when the order changes, then the architecture has to reflect that. So even if you have no interest in coding, if you're interested in computer science, you may find the architecture of this system interesting just in its own right. And if you're not interested in either of those, I'm going to start with a super brief overview of what is Hashgraph. I will show you a demo of our apps running, and then I'll talk about the architecture, the API that we provide you when you're writing apps, and then actually go through the code of a Hello Swirlds. So that's what we're doing over the next hour. I will leave a few minutes at the end for questions, but because this is a how-to kind of a thing, feel free to shout out questions while we're doing it. I think it would be silly to wait to the end of the hour and then have questions. Okay? All right. And don't just raise your hand. These 2 lights blind me, and I may not see your hand, so just feel free to yell. So, what is the Hashgraph? The idea is we want to have a system that doesn't have a central server. It's purely peer-to-peer. Every member of the community is running the same program, and they're all talking to each other over the internet, well, through TCP/IP. You can run them on the same machine if you want, and they just talk to each other through TCP/IP on the same machine. But you can also run them over the internet. And as a group, they come to distributed consensus. So as a group, they come to a consensus on what are the transactions that have happened and in what order have they happened. And then how does that affect the state of the world? And what should they show their user? So they're coming to the consensus on what this shared world is and how it changes over time, as if you had a central server, but there's no central server. It's distributed. And that gives us distributed trust. If one member is evil and attacking the group, they can't. They can't change history. It's immutable. They can't influence this order. The order is going to be influenced by when the community as a whole receives something, not by one person trying to influence the order. They can't stop us from making progress. They can't stop us from communicating. One bad actor can't do anything. In fact, even if just under 1/3 of all the members are colluding and trying to be bad, and if they control the internet, they can't do anything bad. Well, they can turn off the internet. But aside from that, they can't stop us from making progress. They can't stop us from reaching consensus. They can't influence the consensus to be something it shouldn't be. They can't change history. And then I'm just going to put a fairness bullet, because this is what enables things like building a stock market on this ledger. By the way, stock market people are very interested in ledgers right now, blockchain and Bitcoin and whatever. But what they're talking about is clearing transactions, not matching transactions. Basically, they want to have a traditional server that matches people up and where fairness and order matters. And then once they decide what transaction is going to happen, then they use the ledger to permanently record it for posterity so everyone knows what happens. What we have here is a system that can do both. You might as well use this system to do the stock market itself because it's fair. So we have fairness. So that's the overview of Hashgraph. Here's a picture that I've shown twice. I've shown once, and Patrick showed once today. The important thing is that in blockchain, you end up chopping off all those little branches. There's wasted effort, and you have to slow things down so that it doesn't start forking off new branches faster than you can chop them off. In Hashgraph, all the different branches are fine. It can branch all at once. It can branch 100 times a second per person, and it just gets woven together into one big structure. We never chop anything off, and so we don't have to intentionally slow it down. That's all I'm going to say about Hashgraph. Hashgraph is invisible. It is done for you in the software. So I'm not going to talk about how it works anymore. All you need to know is that you build your app on top of a platform that is going to magically talk to its peers on all these other untrusted computers, and they, as a community, are going to come to a conclusion, and then that conclusion is going to be fed back to your app. That's all you have to know for this. If you want to know actually how Hashgraph works, either come to the session I just gave that's too late now, or go to our website and read some papers, or wait a few weeks and the recording of that session will be online. Or come talk to me. I like to talk to people. This is one of the demo apps you get. You get this app, you get the source code for it, and this is a stock market, little tiny stock market. On the screen here, you'll notice that there are 4 sections of the screen. Those are actually 4 separate windows run by 4 separate copies of the program running, and they're talking to each other through TCP/IP. To do the screenshot, I had to run them all on one machine, but I've also run it on multiple machines, and they talk over TCP/IP from machine to machine. So these are 4 different members of the community. You'll notice that the 4 pictures look identical, and that's because we have consensus on what happened. Within one of these regions, you have the 4 columns. One is a transaction number. Then you have who did an ask, who did a bid, and when a trade actually happens, and it tells you who did the trade. So in a stock, and this is all a stock market for one stock, and people are doing asks and bids on the price that they're willing to pay for one share, or the price that they are willing to sell the share for, or that they're willing to buy the share for. This community decides, if you try to buy it and I try to buy it at the same price, which of us was first? Who gets it? The community as a whole decides that. And then that last column, trade, is the consensus on, at the top there in the upper left, it says CA 1.02. Charlie sold to Alice a share at $1.02 because the community decided that Charlie was the first one to match Alice, or maybe Alice was the first one to match Charlie. Whoever was first, the other one was the first one to match them. And so the trade happened. So here it is running. It actually worked. Amazing. And you can just see that they're staying in sync. They all have the same thing. The 4 columns are still the same. Right now, we're seeing about 50 transactions a second. And they're just, as a community, ensuring the fairness. So the most interesting thing here is that the fairness is happening, which you can't see. But the second most interesting thing is they're staying in sync and they're talking fast. Transactions are happening quickly. So this is there it is, 30-second video of that demo, and you'll get the source code for it. The source code's not very long. And then here's another demo that you get. This one shows some other properties. So this is a game. You don't usually talk about putting a multiplayer game in real time on a blockchain, where every move of every player is being recorded in real time, like an MMO. Every time you take a step, it's being recorded in the blockchain. But we're fast enough, log is slow enough, you're going to be able to see that. In this game, I have 8 instances of the program running, talking to each other through TCP/IP. So we have 8 different IP addresses being used, and that's why we have 8 different vertical stripes. Within a stripe, you will see 8 colored little squares and a red little square, or a red mark. The red mark is the goal. The 8 colored marks are the various players, and the black one is this person. So this first one is Alice. The black is her. The second one is Bob. A different one is marked black because, the Bob one is marked black, not the Alice one. And what you're going to see is the group of them going to the goal. And so 10 times a second, I make each player do a move, and you can see that the whole group of them are moving to the goal. Right now, I have an AI controlling each of them, and it just says, walk straight to the goal. Whoever gets there first gets a point. But this program also is set up so that if you hit the arrow key on the keyboard, you will actually take control of it. It'll stop moving under AI, and you can move it around yourself. And so you can play with it and just see how responsive it is. Use your arrow keys to move around and see how fast you move. And then look at the other windows and see how fast other people knew that you move. It's actually fun to play around with this and see visually lag and bandwidth and throughput and all those nice things. So this is the game. Very simple game. Everybody runs around and tries to get to a goal. There's other apps also that you get. One's a Hello Swirlds, and we will show you the source code for that in a second. OK. So let's talk about the architecture of this. And I think just from a computer science point of view, it's just interesting, the architecture of how you build your app. The platform, the browser, is like an operating system that these apps are going to run on top of. And just like an operating system technically has the kernel and all these processes running under the hood, and then it has the user interface with the windows and the mouse and the menus that you interact with. So we have one, like Microsoft Windows really is two parts. There's the part you can see and the part you can't. Same thing here. You get one executable that you run, and that's your browser. But the browser actually has inside of it this platform. So the platform is the kernel. It has a bunch of processes running. The browser is the thing that tells you, here's the apps you could install. Please install them. I'll install them now for you. Which one do you want to run? OK, now I'll run it for you. So it's very much like an operating system. And this is free for download, and it comes with the SDK, and you can also get it by itself soon. Not yet, but go to our website and you can sign up for it. Now, of course, what we want to do is build an app that can run on this platform. So here's your app. You're going to build this app to run on the platform. And your app, when you build it, has two parts. So the app has two classes that you need to write in Java. When you write an app for Swirlds for this platform, you write it in Java. And it will run in a sandbox to protect the user's computer from malicious stuff you might do. And in Java, you need to write two classes that are important. You can write lots of other classes, too, if you want to, just good software engineering. But there's two that the platform cares about and will talk to. In the API, I've given you two interfaces, Java interfaces, and you have to implement those two Java interfaces. So if you're a Java programmer, all that makes sense. If you're not a Java programmer, don't worry about it. You just have to make two chunks of code, and they have to follow what I tell you to put in them. And if you follow what I tell you to put in them, then the platform can call those two and can interact with them. So you have to write a main and a state. The main is your main program. It's where your main program loop is. It's the thing that pops up windows and shows them to the user. It reads the keyboard and the mouse from the user. It does all the calculations, some of the calculations, but it does all the user interface stuff. It's your main program that makes the things happen in general. If you wanted to write a server, it's the thing that is the server that listens to a port and goes out to the internet and gets data from people. The main is your main program. But you also have to have a second thing. And that's the state. And the state, we'll go back. The state remembers whatever's in your program that's supposed to be the shared state that we're getting consensus on. So for a distributed management system, the state is the list of current sessions. That's the state. And what my main program does is it says, hey, state, I need you to add a new session. We've just started a new session. Or I need you to delete a session. So the main is going to be telling the state basically to change itself in various ways as the sessions change. If this were cryptocurrency, the state would just be how much money is in every wallet. That's it. And then the main would do the things like say, hey, please move money from this one to this one, and so on. In a game, the state is, in the game that I just showed you, the state is where are each of the 8 players on the screen, and how many points does each of the 8 players have. So the state is a fairly small amount of information, and it's the thing that we want the whole community to agree on. If you have any local information, like the user just says, I want this color scheme in the browser right now, that you store in the main. It's only the stuff that has to be shared with the whole community and agreed upon by the whole community that's in the state. But the main doesn't talk directly to the state and give it changes to make, because that'd be bad. It would only change your local copy. The whole point of state is that it's in sync between everybody. So here's how it works. Main, when it decides that something has to happen, so main perhaps has decided in a distributed session management system, we need to create a new session. The user's authenticated, I'm an IDP, I have the authority to do this, I can digitally sign it, I can convince the community to do it. It is time to officially say that session number 42 is started. And I want the state to remember that session number 42 is a real state and it's not yet logged out. What you do is you create a transaction, which is just a little string of bytes that encodes, I want session 42 to get started, please add it to the list. What's the format? It's whatever you want. Because what happens is that transaction gets passed to the platform, which passes it back to the state. Oh, you have a pointer. It passes it to the platform, which then passes it back to the state. So the way your main changes the list of sessions is by creating a little transaction that will say, please add a new session, and it gets passed indirectly back to the state, and then the state adds that new session. And so you can use whatever format you want to encode your transaction, because you're the one who wrote the code that makes it, and you're the one who wrote the code that uses it. So whatever language you want to make up for your transactions, you can. You probably want to save bandwidth by making it fairly concise. So that's interesting architecture, that we have to split the program in two, and one half talks to the other through these transactions. On the other hand, talking from state to main, you just do method calls. You can actually access its internal variables if you want to. So say main wants to know the entire list of states, the entire list of sessions in a DSM system. If you want to, you could write in your state a method that says, hey, return the entire list of all the sessions. And main just calls that method on the state. Main has a reference to the state, and it just calls it, and it gets all those sessions. And that's it. Often in a client-server system, you have to be very careful about what data you're sending back and forth in both directions to be succinct. One great example would be in something like a game, like a multiplayer game. The client has to send the server what moves the player is making, and the server has to send back to the client the entire state of the world, which may be this big three-dimensional thing. It's gigabytes of data. And so they have to send diffs to it, and it's very complicated. In this architecture, if there's some gigantic data structure in here, main can just read it directly. Reading that giant data structure is very easy. Changing the data structure, you have to send out a transaction, and it comes in to change it. Does it make sense? You split your program into the main thing, and then you have this little shared state. You have to be careful how you change it with these transactions, but then you can read from it anytime you want, and you can just call methods and read from it. Now, why are we splitting it that way? Well, because we want consensus. I don't want to just change my state. I want to change my state in a way that everybody's state will change that way. And so when the platform gets your transaction, it passes it on to your state. But it also sends it out to this platform running on all the other computers in your community. So you set up a group of computers that are running the same app that are all in the same shared world. And anytime one of them does a transaction, it goes to all of them. And so all of them learn about the transaction. And so what's this line then? This line is where the platform tells the state the transactions you made up and the transactions that everybody else in this shared world made up. And so all the sessions will be there, the sessions you created and the sessions other people created. And then in your state object, you just implement code to enforce rules. If some people aren't allowed to create new sessions, you just don't add them to the list when they try to do it. You look at the transaction and you say, oh, that's a nice transaction, but you don't have the authority to create a session. I'm just going to ignore it. I'm not going to add it to the list of sessions. So all the rules of the community are enforced by the code that you've put in your state. That's all a rule is. It's just saying who's allowed to change the state of the world and who's not allowed to change it, and what are the rules for how it evolves over time given the events that have happened. Yes? Does that mean that every instance of the state in the community has to have the same code, or you get integrity problem? Absolutely. because everybody's running the same app. And an app is a main and a state. So everybody should have the same main and the same state. Yes. Technically, you could give people different mains and it wouldn't hurt anything. But practically, you want them to have the same main also. So it's like if we're going to do a Skype session, everybody has to download Skype. You can't download Skype and I download some other client. That wouldn't work. We have to have this interoperability thing. So you write your app and you give everybody the app and they can communicate. Also notice I talked about the community. If you write a DSM app, you've written one app. You could have a community of people using it to manage one set of sessions, and then an entirely separate community that doesn't talk to them, that's talking to each other to manage a different set of sessions. Yes?
So does the platform have some mechanism for updating the code in the state so that you can synchronize an update and you don't screw up the transaction stream? If I want to switch the system.
Yes. So right now, the code isn't implemented to do the updates, but the way the updates are going to work are really cool. The action to update this is really not important for this session, but it's so cool. The action to update the code itself is a transaction. The community will decide at what exact instant in time to switch from version 37 to 38, and then everybody in lockstep jumps from 37 to 38 at the same instant so that we always are applying the same rules. I love that. And it's irrelevant, don't worry about it. Yes?
So what happens if, like, say...
And that's not implemented yet, but that's something we were going to have, is this ability.
What happens if, let's say, one instance of the app goes down and then comes up? How does
Yeah.
the catch-up work back to that consistent state in the other instances?
Yes. Oh, I forgot to repeat your question for the video and for everything. So you're asking, if somebody goes down, then when they come back up, what do? If they're down for a little while, they get the Hashgraph because they're gossiping. So you go down for a little while, you come back up. The very first person you gossip with, they send you everything that they know that you don't know. Well, it turns out it's a lot. And so they just send you all those transactions. They send them to you in the order from oldest to newest. So in your internal Hashgraph, it's growing properly. You don't kind of build some nodes hanging up here in midair that aren't connected to anything. You start at the bottom, and every node is connected to it, the ones below it. And once you have caught up, now you're a full member of the community, and you're caught up. You won't really be contributing to the community until that sync ends, and it may take a while. That's okay. Now, if you're down for days, there are mechanisms where we can actually remember a state and get everybody to sign it, digitally sign it in the community, and then throw away all those old transactions. We can actually throw away all the old parts of the Hashgraph. And that's, in some applications, a state is far more compressed than an eternal history of all transactions ever. You could imagine a cryptocurrency. The history of all the transactions will grow without bound as the universe gets older. But the state is just how much money is in all the non-empty wallets at this moment. And eventually we'll reach a steady state where the size of that isn't changing. So in that situation, when you're throwing away the old parts of the Hashgraph, when you wake up after Rip Van Winkle, you wake up after a year, what you do is you get a signed state from somebody. And you know it's valid because it's signed by the majority of the community. And then you sync with someone, and they just give you the events that have happened since that point. So that's a cool mechanism. But aside from that, you get the catch-up automatically. It's inherent in the gossip protocol. When you wake up, you get everything you missed. And
Follow-up question, sorry. So does the gossip happen through the platform or the app directly talk to each other?
Good question. Does the gossip happen in the platform, or do these guys gossip? The gossip is purely right here. It is something the platform does. It's invisible to you, and you don't have to worry about it in your app. So in your app, all you see is I send out the transactions for changes I want to make to the world, and I get back a much bigger set of transactions which reflects my changes and everybody else's changes. And that's it. You don't worry about gossip. You don't worry about hash graphs. You don't worry about consensus. You don't worry about timestamps. It's all just sitting there for you right there. And it's the platform that runs the hash graph algorithm and the consensus algorithm and does all the hard stuff.
So along those lines, with the platform, how do you sync timing? You just mentioned timestamps. To get consensus
Yes.
in our world, that's always a problem with machines having different timings across regions.
Exactly. So the way that it works is that when you send out an event we end up with a community consensus on when that event was received by the community, which is the timestamp of all the people's computers, just whatever their computer's clock says, that list of times, it's the median of that list of times. So basically, when it's reached half the people in the world, that's when it is. And if a few people have a bad clock on their computer, it doesn't kill you. Okay, so it's the median of the community. It's a consensus of the community. Okay. Yes?
Is there a required minimum number of participants for the system to be reliable?
There is. Is there a required number of participants for the system to work? And the answer is yes. You can tolerate less than a third being evil or asleep or turned off or crashed or whatever, and you continue to make progress. If a third or more are evil attackers or have lost their computers, then you're in trouble. And there's actually some math theorems that say you could never get a higher number. That 1/3 actually comes out of there's theorems that say the best you could never do is a 1/3. However, if we're not talking about evil attackers, if we're just talking about people turning their computers off, then when everyone turns their computers off and only a few people are up, you will not reach consensus, but you will still gossip all transactions. So if you were playing that little game thing there, you would at least know what all the other people's transactions are, but you wouldn't exactly know the community consensus on their order. You have to wait until 2/3 of the people have awakened, more than 2/3 have awakened, and then you get the consensus. So there's two different things here. Do I know what events have happened, and do I know the consensus on those events? The consensus requires 2/3. The just knowing it doesn't require any minimum, but if we're worried about attackers, we need 2/3 to be honest.
But how about the absolute number, not percentages? Like, as 1/3 has to be minimum of 3? Like, it has to be at least 6 instances or 10 instances, or is it?
Okay, so you're asking what does the 1/3 mean? I'm talking about the 1/3 of the community. So what we have,
And I'm asking about the size of the community. What's
yes,
the minimum size of the community?
minimum size of the community is 1. Maximum size is however many you want. And it should work for 1,000, fine. If you go beyond that, I'd go to a hierarchical system with sharding. But this community size. And whatever that size is, divide by 3. Your answer may not be an integer, but whatever that real number is, you need just more than 2/3 of that number to be, multiply it by 2/3, and that may be a real number. You need just the next integer above that. That's how many people have to be participating and honest and so on.
And the communication is through TCP/IP?
Yes, the communication is through TCP/IP. Right. The community can grow dynamically, yes. And so there are rules enforced for who's allowed to join, and those rules are implemented in this. So you get to decide how that works. So you can build a permission system where you just say nobody can join, or you have to be signed, have a signed note from a central authority to join. Or you can have a non-permission system. There's lots of different things you can do. Yes?
Is there any concept of a member leaving the community?
Yes. There's several ways. But again, is there any concept of a member leaving the community? Absolutely. What you can do is you can have this one deciding that it is appropriate for a user to leave because they have cheated in some way, or because we've had an election and the group has voted to kick them out. This can, in its state, can calculate various rules for what would make people leave. The main can read that and say, oh, I see, that person needs to leave. Or you can just log into your computer and say, I don't want to be part of this community anymore. And main says, OK, I will do a logout for you and make you leave. Yeah. And it's not a logout. It's, I want to quit this community and never come back. That's what we're talking about. And then that transaction goes out and it goes to the community, and the community decides a consensus on the exact moment in history at which you left. And then when I say 2/3, I'm talking about 2/3 of all the votes up to that moment. But then after that moment, it's 2/3 of a smaller community. OK. Which is funny. Consensus needs 2/3, but I have to have consensus to know who the 2/3 is. So that's it works out very nicely. Yes?
So is the communication between the state and the main a push, pull?
It is a pull. Good question. Is the communication between the state and the main a push or a pull? The main is a thread. The state does not have a thread. It just sits there and waits for its methods to be called by the platform and by the main.
So if a member quits,
Yes.
then unless the main asks for that information, state is not going to supply it.
Exactly. If you want to tell your computer, I want to quit now, then the main on your computer will send a transaction to the world saying, I want to quit. On the other hand, if you cheat, then everybody's state is going to calculate, and cheating, I mean violating the rules of the community. It's whatever rules you made up when you wrote your app. Then maybe the state will decide, hey, we need to kick Alice off the island because she just cheated in some way. And then everybody's main is going to start sending out transactions saying, hey, let's get rid of Alice. Or whatever. Okay? Okay. I was actually afraid we wouldn't have enough material to fill the full hour. How foolish. By the way, I keep saying that the main has this GUI and I have a user sitting in front of the keyboard interacting with it. You can build a headless system, of course. In fact, for DSM, Ping built a headless system. In a headless system, main is running this main loop, but it doesn't have any windows. There's no keyboards involved. What it does is it listens to a port and talks to people out on the internet that tell it to do things. So it's acting sort of like a server. It's like a database server. And so this whole app can be a distributed database that people out on the internet can ask the database questions and tell them to make changes in it. And then the main takes those and turns them into transactions. So notice that these were all transactions, but these two blue arrows are just arbitrary data. This is just method calls and internal variable accesses. And this is just whatever protocol you want to come up with, which Ping has now submitted to a part of it. I think actually this piece they didn't submit yet, but I don't even know. Anyway, you need a protocol, and Ping has or will be submitting that piece right there. Okay. Ooh, why are there multiple states? So this is another thing that's interesting. These are things that happen because we're doing a real-time consensus system that you just don't have in any existing software because you don't do real-time consensus systems. I told you you have to write two classes in Java, one for main and one for state. But you don't instantiate them. The platform instantiates them. And in fact, the platform's going to go crazy and instantiate several copies of your state. Here's what's going to happen. You know, we want to have the user seeing the effect of all the transactions in whatever order we receive them right away. You want to see that. If you're playing a game, you want to see that right away. If you have a session logout and somebody says, if the IDP sends out a signed message saying, I'm the IDP that created this session, it is compromised, please log them out right now. Well, you want to know that right away. You don't care about trivia like where does that fit into history. You want to log them out right away. So you want to know about transactions immediately. You don't want to wait. So what happens is when new transactions come in, they are sent to the state immediately. These transactions may not be in the consensus order. Someday, the community may decide, oh, yeah, those transactions should have been in a different order, and there's this new transaction that should have been stuck in the middle there. Someday it may change. But for the moment, the platform is just going to send the transactions to the state in the order it gets them. And the state will continually be updating its internal state to reflect that order. Now, in parallel, at some point, the platform's going to say, you know what? As a community, we've reached a consensus. The transactions should have been in a different order. So here's what I'm going to do. I create a different state over here. I instantiate a new state, and I feed it those transactions in the correct order. And that may take a while, but it happens in the background. And eventually, this new state catches up with the present. So now the new state and the old state both have seen all the transactions. But one of them has seen it in an order that is more accurate than the other. Then the platform says, OK, I now declare that this is the official state, and this one I'm just going to throw away. So when the main talks to the state to get the data, frequently the main calls an API call that says, hey, could you give me a reference to the current state? So whenever I'm going to talk to the state, I'm first going to ask the platform, give me a reference to the current state. Give me a pointer to the current state. And that way, When this newer state that is new and shiny and has the transactions in a better order is finally created, it'll just get swapped in, and the next time I access the state, I'll be accessing the new one instead of the old one. Very straightforward. And so we would need two different states, the current one and then the one that the platform is building up. Now, of course, I just described that as sending an infinite number of states into transactions into this guy. We can do further things where we take all the transactions that have a consensus, feed them in to a state object and get that consensus state, and then we make a copy of it and hold that aside and add more stuff. And then later, we only have to start from a copy of that consensus and add in just the last few transactions. Yes?
So when the main calls the state, does the main get the information for each transaction about whether it is consensus or not yet, so that it can make decisions on that basis?
Excellent question. The question was, does main get to learn which transactions have consensus and which don't? The main doesn't see transactions, it sees state. But the state does get told. Every time it's given a transaction, it is told, this is a consensus transaction or this is not a consensus transaction. And so if it wanted to, it could color code results on the screen, saying the red ones are the ones I'm not yet sure about. You could even make it throw away all the non-consensus ones and just show you consensus on the screen. So the state gets to decide what it wants to do based on whether it's consensus or not.
And in your market example, you only did matches for bids and asks that had achieved consensus.
That's true. What you saw in that video was just consensus, right?
So building on that,
But I'm sorry, but the game was not. And if you looked closely, they sometimes got out of sync and then jumped back into sync. Yes?
so with the stock market example, when you get the latest state, is it persistent or is it all in memory as you going through talking to different apps?
Excellent question. The question is, hey, is this state persistent or is it in memory? And the answer is, you can keep it in memory if you want, or you can write it to a file, or you can write it to a database, which is actually in a file. So you can use databases, you can use files, and you have it. Now, you notice a little while ago, okay, we're getting to stuff that's later in the talk, but you notice a little while ago that I mentioned that sometimes the platform has to make a copy of a state? It calls a method to the state that says, here, make a copy of yourself. Well, wait. If I'm writing my state to a file or a database, would I have to copy my entire file system or my entire database? What we really need is a data structure that allows you to very quickly copy a file or a database. Actually, that's the next slide, isn't it? Yes, excellent lead-in, thank you. Inside the state, you have your variables. That's just, in RAM. You also have file systems and databases. But we provide you a class called file system fast copyable and database fast copyable. And what it looks like is an entire file system, like a little hard drive that has a directory tree with files you can put in it, or a database that looks like a database, a relational database with tables and rows and columns and things. And then there's a command on it that says make it a duplicate of the entire thing. Take my gigabyte database and make a copy of it. Take my terabyte file system and make a copy of it. And in a nanosecond, it comes back and says, OK, here's your copy. Now you have 2 copies of the database, 2 copies of the file system. And they look like a byte-for-byte identical copy. And if I ever make a change to one, the other one doesn't change. It's like they're 2 separate copies. Now, of course, under the hood, we're doing, we're actually doing some tricks. So it's actually one thing. It's only when you write to it, it's a copy-on-write mechanism. It actually makes the actual copy. So we don't do the copy immediately. But it looks like you've done the copy, which is another thing I find interesting. When you're writing apps for a distributed consensus system that's real-time, which means we're going to have to do this thing with copying states, now you need a fast copyable file system and a fast copyable database. And you would think that such things would exist, and they don't. In the database world, everybody has something called a snapshot, which is like making a fast copy, which does the same trick I just said, except you get the snapshot and the original, but you're only allowed to change the original. You're not allowed to change the snapshot. So we've written a whole database system that allows you to change the snapshot, too. So that's what we have here. Boy, these are good questions. Yes? Oh, this is just whatever your state decides to write to it. So your state, it's just one of the things that we provide you.
If you had an audit requirement, you could write the transactions in there?
Sure. Yeah, you can. So you might think it'd be nice to store everything on the file system because if my computer crashes, I don't want to lose it. On the other hand, you might think, I don't really care. If my computer crashes, I'll just download it at my next sync from somebody else. Or you might say, I want to save bandwidth. I'll write it to a hard drive. This gives you a mechanism, the file system and the database that are fast copyable, gives you a mechanism to store it to your hard drive. So if you crash, you can recover. But at the same time, do instantaneous copies. It looks like you've made a copy instantaneously. OK. That's the end of the architecture part of this. Boy, feedback's weird. I'm sorry? Go ahead.
So, looking at this a little bit more maliciously,
Yes.
what stops this architecture from being used as a massive DDoS? Just effectively making each of those apps just little zombie bots, and then it's the next anonymous attack.
OK, so if your attack scenario is that you've written an app that's so much fun, everybody wants it. So here we're probably talking about a game. And kids around the world all download it. And in addition for it doing all this communication that it's supposed to be doing to play the game, in the background, it's DDoSing people that you don't like. Is that the scenario? Sure. OK. In that scenario, yeah, that's bad. OK. However, I will point out that it's running in a sandbox, so the user could turn off the ability to go to the internet for that. We might turn off this ability to go to the internet, but the typical kid won't do that, so maybe it's off by default. But yeah, anytime you're running software, it can be a Trojan horse and do bad things. What we do have, though, is that it's in a sandbox, so it can't go erase your hard drive. It can't go read all your private data off your hard drive. It can't fill your hard drive with terabytes of data because there's a hard limit on how many bytes it's allowed to write to the hard drive. Those sorts of things. Yeah. But yeah, if you write malicious software that is part of a botnet and the kids playing the games don't know it, yeah, that's bad. Same thing with current games. Yes?
When Maine writes a transaction, is it immediately available in the state, perhaps without consensus?
Yes.
Does it have to account for?
Let me repeat the question. Excellent question. When Maine writes a transaction to the platform, is it immediately in the state before we have consensus? Yes. In fact, the code says the instant I get it in the very method where I got it, I instantly send it off to the state. And then I send it to the rest of the world, and then eventually we get to consensus, and then eventually I'll have some copy of the state where I send it in the right order. But you get it immediately. And it's not just true of things you create. Anything I hear about in the gossip protocol instantly ends up in the state. And then later, we'll worry about what order it should have been in.
But is it in the state before the method finishes that wrote the transaction? You know what I'm saying?
Yes, actually it is. Yeah, that's actually true. It's in the state before the method completes. Yes.
So I have a follow-up question to that. So if it's getting it before it's in consensus, is there a correlation you can use with the state to determine whether the same state you've seen previously that wasn't in consensus all of a sudden is in consensus?
The question was, can I tell how much of the state is in consensus?
No.
No.
So you get the state and it's not in consensus, right? Let's say Maine gets that for some, gets that right. And then later on it becomes in consensus. Is there a way I can correlate the fact I've seen the state already in
Oh.
consensus?
Oh, yeah.
Now that it's in consensus?
Oh, yeah, yeah. So the question was, is there any way that Maine can see that that the state has changed in a weird way because it was out of consensus and now it's in consensus? Yes, and in fact, in that game application, you'll sometimes, the red goal jumps to a new pseudo-random location based on who reached it first. And there's a case, I think, in that video even, where you'll see it momentarily flicker between two spots. And what you are seeing is history changing before your very eyes. First, it thought Alice reached the goal, and it jumped over here. And then it said, oh, no, I'm sorry, Bob reached the goal before Alice, so then it jumped over here. And then it flickers. So yes, Maine can see that just because the state changed in a weird way. Of course, you can also just have Maine ask the state, and you can make your state remember in some way which ones are consensus and which aren't. It's however you want to write it. But yeah, the user gets to see that. That actually happens in MMOs and other things. The talk this morning said that my original interest was in games, which actually is not the case. It was in consensus, collaboration. I want to be able to connect to people over the internet and collaborate with them and set up shared worlds where we have shared files and we can collaborate with each other and we can video conference and we can have enforced rules and then play games too. That was the genesis of all this stuff, not games. But I talk about games a lot because if we're talking about real-time stuff, the gaming industry is right on the cutting edge. Not the cryptocurrency people, it's the gaming industry because that's where tiny lags matter. Stock markets also are on the cutting edge of that. Okay, that's the end of the architecture. And actually, that's the most important, this slide right here that you're seeing is the most important part of the whole talk. We've now finished building it up, and this is the most important part of the whole talk. If you understand this, and these questions were really good, if you understand this, then you understand the principle of how to build an app in Swirlds. And yes?
You didn't talk about the browser? Is that like a
Yeah.
Chrome or something?
No. So Chrome is a browser for web pages. This is a browser for Swirlds apps.
Oh, it's a special Swirlds browser.
Yeah, so all it is it's a program that tells you, here are the apps available, and then you can load them in, and you can say, I want to run that app, and then it runs. It's like an operating system for apps. Okay. And it also has the ability to read in a config.txt file, if there is such a file there, and then you don't have to interact with it. It just knows, I need to run a simulation where I run multiple instances, and they talk to each other through TCP/IP on my machine. It's great or on multiple machines even. Great for running simulations easily, or for controlling a headless system. Because in a headless system, you don't have the browser, the visual part of the browser at all. So the browser takes care of all that stuff. I should also point out, I have told you lots of things using the present tense. This is what it does. Some of the things I've described are coming someday, but they're not part of the platform right now. So the platform right now is just an early pre-alpha version. It's very simple. Not everything I have said is in it, but the core parts are there. Yes? Yes, go ahead. Can a member participate in more than one community? Absolutely. You can either take turns if you want to devote all your bandwidth to one community, and then you just turn off your program. You don't have to log out or anything. You just turn off your program and stop talking to them, and then start up a program talking to a different one. Just your app was talking to this community, now you make your app talk to that community. That's one thing you can do. Or you can run two apps in parallel, and now each is talking to its community, and they're kind of fighting for bandwidth on your machine. But if you have enough bandwidth, then they both talk to their communities. A single instance of the app, but you could run two instances of the app and talk to two communities. Right, so you could have one DSM app, but you run it twice in parallel, and now you're talking to two different DSM communities. I didn't repeat your question for the video, but you just asked, can you talk to multiple communities at once? Yes?
You have more than one application use the same community, the same state in the same community.
Can I have more than one application use the same state in the same community?
You have a headless app, the same set of states. You have another app that has a UI, so you can see what's going on.
I understand. The correct way to phrase it is there's only one app. And that app, when it launches, looks in the config file to tell it whether or not to put up a GUI for the user to use on the screen or to run in the headless mode. So it's one app that has two modes. Make sense? OK. I don't even remember if I repeated your question or not. I have 11 minutes. Go ahead.
The platform, is it a library, a runtime? What is it?
Yes. The platform is a library or runtime. Yes, it's both. So here's what the platform is. The platform is a process that is actually running, a whole bunch of threads that are running, that are constantly talking to the community and gossiping, and that are constantly doing this trick of instantiating new states and copying things across and feeding them transactions. That's what the running part of the platform is. It has multiple threads that do all those things. In addition, it has an API. For example, it has two Java interfaces, one that defines what method you're supposed to put in your main, and one that defines what method you're supposed to put in your state. In addition, it has useful things, useful methods, and also whole useful classes. Like it has the file system fast copyable class and the database fast copyable class. Just useful things for you. So it has all that stuff, similar to an operating system. It has a core that's constantly running, like a kernel, but it also, and processes that work on it. And then it also has a bunch of libraries that are available to you.
And where does it run?
Where does it run? On your local computer. Oh, yes. So it's Windows, Linux, and Mac. Yes. And it's fun to test it, with the Mac and the Windows talking to each other, because usually they hate each other and they don't talk. The system as a, you asked, is it resilient? The system as a whole is resilient because, that's the whole point of the Byzantine convergence stuff.
I mean, not in terms of the community, but the platform that hosts the community. How can you make sure that it's always available, never fails down? The runtime, does it have to run in multiple instances itself?
So normally, this program that's the browser and the platform, you have only one instance of that program running on your computer. I'm sorry, you have one instance of the browser running on your computer. Unless you're doing one of these experiments, you don't have multiple platforms. So there's just one thing running on your computer at a time. Yes?
So the database box, is that a proprietary Swirlds database, or is that an abstraction for just any off-the-shelf database?
Oh, good question. It's an abstraction, which we have our thing behind it. And I seriously hope that the database community will eventually add this feature. We've put enormous effort into building this feature on top of the Java database. But there's no reason that Oracle couldn't just add a new feature to their database that says you can make special snapshots that you're allowed to change. I really wish they had. But the reason they haven't done it is because no one's ever had a use case for it. No one's really needed a fast copyable database right till now. They've needed to be able to make immutable copies. That's what snapshots are. All the commercial databases do that. But they've never had a need for this weird thing where you make a copy and then you can change both copies. And I think it wouldn't be a whole lot of coding for them to do that because they've already written all the code for the snapshot. And so maybe the database community will eventually do that, in which case you use theirs. And you could use theirs with our front end to it, or you could just use theirs, period. You don't even have to use our API. It's just something else. I have 8.5 minutes. I think I'm going to go through the next few slides. There's only 3 slides left, but I did want to show the code. So you have to implement, this is the Java word implements, this thing called swirled main and this thing called swirled state. So we have 2 things, and if you're not familiar with Java, the purpose of an interface is it requires you to write certain methods. So here's the method you have to write, here's the method you have to write. The API may even change in the future, but this is basically what it's going to look like. And I'm calling this example main and example state. That's the class that we're pretending we're making right now. So we're writing a new app called example, and we've written example main and example state. They each have a few methods they have to call, but the important ones are these. Main is going to have a run method, and there will be a thread that is started up whose job is to run the main method. All your stuff happens in the run method, and when you're finally ready for your app to shut down and to go away, then you exit and return from that method, which is how Java does runnables. That's how things work right now. So run is going to run in its own method, and it is your main program. Run in its own thread, and it's your main program. In the state, obviously, the most important thing is handle transaction. This is when the platform hands the state a transaction, and the state has to handle it. And an excellent question pointed out the fact that one of the parameters is Boolean consensus. It is told, hey, this transaction I'm giving you is actually part of the consensus. All the transactions I've given you up so far, up including this one, are in the consensus order. If you want to tell the user on the screen that it's good, you can tell them it's good. This is something that won't change. Or if it's false, it says, yeah, I don't actually know where this goes in history, but I just wanted you to know it right away, just in case you needed to act on it.
I've got 2 questions. The first one is there a size limit on a transaction?
Okay, is there a size limit? No, you're just bandwidth limited. When you write your app, you're going to decide what size you want your transactions to be.
And the second one is, because there's the main, does that mean that I can't really embed it into an existing server, for example? I have to run
Right.
service or something?
Right. Don't embed this into a server. It can be, however, its own little server thing that talks through TCP/IP to your normal server. And so we've talked about this. This is an interesting question. I'm glad you brought that up. Did I repeat your question? I don't remember if I repeated your question. I did not. The question was, could I just put my server inside of this or put this inside my server? The answer is, don't put a platform inside a platform. The way this is designed is the Swirlds platform is a platform. Your server is probably a platform. Write your code on the server, write a little tiny piece of code in Swirlds, a very small app, and have the two talk to each other with TCP/IP just through localhost, just on your same computer. And so now you have the two programs running on your computer. They're nicely, cleanly separated, and they talk to each other through TCP/IP. That's the intended way of doing this. In that case, the Swirlds side of your program ends up being really tiny. It's really simple. All it's doing is taking these messages that you send from the other program, and all the real work is done in the other program. OK. I'm going to go forward then. Here's what this Hello Swirlds app looks like when you run it. Here's 3 instances running. Here I put the windows overlapping just to make you understand they're really windows, 3 separate instances running. And all it does is it says, hello Swirlds from, and then its name. And there's ways that you can ask the platform, hey, who am I? What is my name? So you can find out from the app, from the platform that. This one's Alice, Bob, and Carol. And then in this example, in this Hello Swirlds, you just print out Hello Swirlds from Leemon, and then you send out just one transaction. You're only going to send out one transaction, and it's your name. So you just send it out, and look at this, received, Alice. What it does is it prints out all the actions all the transactions that it has received. And there was the question, do you receive instantly when you send it out? Yes, you do. Which is why you'll notice in all 3 cases, the first line is, well, the only transaction I know about is the one I just sent out, because I just woke up, sent out a transaction, and I immediately have my own. And then there's just this loop that runs forever that listens for new transactions coming in and stores them in a list. And you can see there's this list. First he knew Bob, then he knew Bob and Carol, then he knew Bob, Carol, and Alice, and then he stopped printing things because no new transactions came in and the order never changed. In this particular run of the program, the consensus order was Bob, then Carol, then Alice. Every time you run the program, you get a different consensus order. Furthermore, look at what happened with Alice. At one point, she had received Alice, then Bob, then Carol, and then a little while later, the platform said, oh, I was just giving you those not in consensus. Now that we're in consensus, I realize it should have been Bob, then Carol, then Alice. So this is a case where the platform had spawned off this new state and then fed it the correct order. And that's it. So let's look at the code for those two. 2 slides left with the code. Here's what your run program does. This is your main program. You get your name. You get it from the platform. Then you create your transaction. And I said we're only going to create one. It's a byte array. And it's in whatever format you want. And what I did is I turned your name into a byte array just using the standard Java way of turning a string into a byte array. That's just built into Java. So you get bytes in standard UTF-8, blah, blah, blah. That's just standard Java. So I took the string, turned it into a byte array, called that my transaction, and sent it out to the world. I haven't sent it yet. And then I printed out hello Swirlds. So we print out that line, hello Swirlds from and my name. And then we called the platform and said, I want a new transaction. I am creating a transaction, and it is this byte array that contains my name converted to bytes. Then the platform does stuff for you. It digitally signs it, it timestamps it, it gossips it, and it makes sure everybody knows about it. And then it works with the community to decide where in history it goes. Then you have this infinite loop. And in the infinite loop, I'm constantly reading the current state, getting a pointer to the current state, a reference to the current state. Remember, you have to do that because the platform sometimes creates some new state and says, OK, now that's the official one. So every time through the loop, I ask the platform, hey, give me the current one. I want to make sure I'm up to date. And then on that current one, just for this example, I made up a method called getReceived. We'll see it on the next slide where I implemented it. You can make whatever you want to get data out of your state. This is how I decided to get data out of my state. I call getReceived, and it returns to me this string, which is that list of names in square brackets with commas between them. So I got that thing that I printed on the screen. And if it is different from the last one, then I remember it and I print it out. Now you notice this is an infinite loop. It could print an infinite number of lines, but when I ran the program just a second ago, you saw the output was only 3 or 4 lines, and then it had reached consensus, and then it stopped changing, so it stopped printing things. And so it then ran forever, never printed anything because it reached consensus, nothing ever changed. So that's it for the run in main. Okay, I have all of 17 seconds. In handle transaction, it's one line of code. Add. That's it. I have an array list that's going to remember all the names I've heard so far. I have an add. Notice I don't have a delete. The state doesn't have to worry about the order changing. From the point of view of one state object, the transactions that come in never change their order. They just come in some order, and I have to reflect them. It's this other state object that gets instantiated that gets the other order of the state. But a given object never has to worry about the order changing, so you don't have to think about the order changing. All you have to remember is, I'm going to be fed a bunch of transactions, and I should reflect them in the order they came. That is the end. I'm free for questions. I appreciate you sitting through a full hour of this stuff, and I hope to talk to you later. Thank you.